Hey, hi everyone, this is Vivek, and in this particular video, we're going to talk about Dilworth's theorem. Now, this particular video is sponsored by Algos, but more about them at the very end. Now, Dilworth theorem is one of those techniques that I personally feel is one of winning recipes, which means someday somebody is going to get a critical rank in some competition due to knowing this technique and or not. Like that's going to be the main decider. And in this particular video, we're going to go through like different types of Dilworth theorem based questions that are generally asked, like all different types that are there. And we will also go through like its very, very close cousin Mirsky's theorem and some corollary related to these things, right? So let's get into this directly. Let's start with the problem. Let's start with a very, very well-known problem, which is known as finding an Elias, right? So let's say you are given this particular set of numbers and in an array, and you have to find an Elias. Very, very simple problem, right? In this case, we can simply do this. Like you can take, let's say, 1 followed by a 3, followed by, let's say, a 6, followed by, let's say, a 9. And that should give you, I think, 4 length Elias, right? I don't think we can do any better than this. Now, let's say the new problem that asks is decompose this particular array into minimum number of aliases, which means we have to make sure that every element belongs to a particular sequence and all of them are like a increasing subsequence, right? And I would not say it's alias, I would say increasing sequences, right? Or increasing sequences. So let's say I take one of the sequences to be this, right? Which we had over here, right? Let's say we try to choose another sequence. Let's say 7, 8, right? And then we can choose and let's say we also extend this to like 10, and then we have to take another sequence which just takes 6, right? So each of these sequences, as you can see over here, is actually an like an increasing subsequence, and we had decomposed the whole array into multiple different increasing subsequence, right? So we have to find it. What is the minimum number of such number of sequences do you need to decompose the whole array, right? And from some idea you can also get this that actually you will try to get more and more number of aliases and kind of get through things in that might be a greedy strategy that you can have in mind, which might or might not work. I will give that to you as a task. That think about a case where, let's say, pulling out the longest increasing subsequences from the array might not leave you with the like minimum number of alias, right? Minimum number of chains in the decomposition of using the aliases only, right? So that's what we are kind of dealing with over here. And how do we solve such problems? That's the question, right? And this is where the Dilworth theorem comes into picture, right? So let's kind of understand the theorem. Now, for this particular video, we will not learn this theorem from the like notions of, let's say, set theory or any like mathematical terms. Instead, we will also skip out proofs and just understand how to apply these in problems, especially in computer programming, right? So first, we need to understand what a poset is, because anytime you're gonna read a definition of this, it's gonna be related to partially ordered set. Essentially, what that means is like you have a relation, let's say this less than equal over here, which between which you can kind of tell that there is some sort of relation between two elements A or B or not, if they are comparable with this particular relation or not, right? And such a particular set on a relation, right, is called partially ordered set, where you have certain relations between elements over here, right? In this case, I can draw some relations between elements that between 1 and 3, I know that 1 lies before 3 and 1 is less than 3. So they are in a relation, right? That 1 can go after before 3, right? 3 and 8 is in relation, 3 and 6 is in a relation, right? These kind of things are definitely like in relation, right? Because we can say that this is both before and is of less value, right? So less than equal to in this particular problem would mean that, okay, uh, like the element, let's say over here, and the index both are less than the corresponding values over here, right? So this is what we are looking at over here. Now, in this particular case, we also have a definition of something called as a chain. Okay, chain is a partial ordered set that is of this particular so we are defining a set over here, right? Which means it's a collection of numbers from this particular thing. In this case, it's going to be the indexes of the elements, right? Those are each of these index elements are one of the elements of the set. Now we have to choose a subset of elements from this which are all comparable to each other. So there is a relation between each and every one of them. So 1 and 3 are related, 3 and 6 are related, right? And even 1 and 6 is related, right? So it has to be sort of this clique in this graph, or they have to be all related, right? Even if you take 10 with this, they are all related to each other because all of them are kind of interrelated, right? Now, if you try to take 9, okay, from 6, 9 is related, from 3, 9 is related, but from 10, 9 is not related. So so 9 and 10 cannot be in the same chain, right? So that's what is the definition of a chain. Yeah. Now, what is an anti-chain? An anti-chain is a subset of elements with no two elements are comparable to each other, right? So that's what an anti-chain is. Like they are like there is no relation between both of them in this case. Like 6 and 3 has no relation, right? Whereas like had there been a 3, had there been a 6 over here, there would have been a relation between these two elements, but right now there is no relation between them. Okay. Another thing we call as width is essentially the minimum number of chains you need to cover S. Essentially, it's the same problem in this case. We have to find out minimum number of chains. Okay. Remember, this was one of the chains, right? This was, let's take another color. This was another chain. And let's say this is another chain, separate, right? So there are 3 chains. So in this case, the width of this particular thing is equal to 3. That's what we are in fact looking for, right? And this is the main definition of the width. And there is this particular second definition which comes into picture for this particular problem, is that width of a finite partial order set is maximum size of an anti-chain in S. Now, this is what we call as Dilworth's theorem. The width of a finite ordered set S is the maximum size of an anti-chain in S. Essentially, what it is saying is, if you're trying to decompose this whole set of numbers over here into a particular into chains, and you want to cover all the elements, the width or the minimum number of chains that you need is going to be equal to the largest anti-chain that you can form. Okay, so essentially we were on this scope, right? We had to find out the width of the finite ordered set. This is what we wanted to find, right? Now, essentially Dilworth theorem makes it go from this to this. Find a maximum size anti-chain in S. That's what now we will be inclined to finding towards, because we now know with Dilworth's theorem that they are actually going to be equal to each other. Now, we have to find the maximum size anti-chain in S. Now, that is something that we can do, right? Like we, instead of decomposing it into minimum number of aliases or minimum number of increasing subsequences, let's say, now we are finding longest non-increasing subsequence. Now, this is going to be this is equivalent to finding a anti-chain. Why is this an anti-chain? Why is longest non-increasing subsequence an anti-chain? Think about this, right? Let's say longest non-increasing, which means sort of decreasing, right? Let's try to find out that this is 1, right? I see this is 1, and then this is there, right? This is these 3. Like I can only like the longest that you can make is this 3, right? So in this case, these 3 form, because think about this, between 7 and 6 there is no relation, between 6 and 3 there is no relation, between 7 and 3 there is no relation. So this does form an anti-chain because none of the elements have a relation between each other, right? Had there been any element which has like smaller value before the other one, there would have been a relation, but in this case there is no relation. So in this case, one of the anti-chains that we can find is of size 3, right? If you try and find out, I think we cannot do better than 3 because we have already established that the minimum number of chains needed is 3. So in fact, the largest anti-chain is also going to be equal to 3 in this case, right? So if we can find out the longest non-increasing subsequence, because in this case, non-increasing subsequences can never have relation among the elements of each other, right? So it is going to be an anti-chain. And since we are finding the longest, it's going to be the largest anti-chain. And based on Dilworth theorem, the maximum size anti-chain that we can find out is actually equal to the minimum number of chains that you can use to cover the whole set, right? So that's what this is all about. And now we converted this particular problem to this over here. This might have been a little difficult because we might, even if we use Elias multiple times, you would have nk sort of log n, where nk is the number of finite number of answers or number of chains that you need. But in this case, finding non-increasing subsequence is fairly straightforward by just modifying the logic of Elias a little bit. Like maybe you can see this array in the other way around, and in the n log n code of Elias, right? You all might know about n log n code of Elias because I've already covered that on my channel. So n log n code of Elias, you can change the, let's say, there is a lower bound and upper bound that you use over there, right? So you can use upper bound instead of lower bound, and that should give you like longest non-increasing instead of strictly increasing or strictly decreasing or things like that, right? So that is what we change over here. Just a small change is there in the code if you kind of go about doing the coding part, but essentially finding this is equivalent to finding this. This is the main use case of Dilworth theorem. Now this looks like a more complicated problem. This is a fairly straightforward problem which has an n-log solution. So we went from a complex looking problem where you had to decompose the whole like set into chains into a very well-known problem, which is finding longest non-increasing subsequence. This is what the power of Dilworth theorem allows us to do. Okay. Now let's take a look at another problem, and that's going to give us more clarity, right? So over here there is a space where persons can spawn from, right? And which means they will like just get into they will come from thin air, some teleportation machine is over here, and the persons can move down or right, okay? And there are some orbs on the whole space, like this is, let's say, a grid, okay? And this is, let's say, 1 till n, and this is 1 till m, right? There's a grid space over here, n cross m grid space, and you have starting at 1 comma 1, you have to go till n comma m. Every person is going to kind of follow this zigzag path which we follow using an down and right moves, right? Now what we need to find out is how many minimum number of person do we have to spawn over here so that every orb can be collected, right? So let's say over here what I can think about is maybe this person can kind of go like this, collecting these orbs, right? Then there can be another person who comes over here and maybe I'm trying to cover like this, right? Okay. Another person comes like this. And for this last one, I think we'll have to spawn one more person. So there would be another person who goes like this. So there are 4 persons would be needed to collect all the orbs. So in this case, the answer would be 4, right? So we need to find out how many minimum number of people need to kind of start from over here and go till end so that all orbs on the grid can be collected, right? And it's an n cross m. And this is what we need to solve, let's say, and let's say n into m is the kind of complexity that we are dealing with. I mean, order n into m should be good enough. Anything more than that would not work. So how do you solve this kind of a problem, right? Well, this is again yet another good idea of Dilworth's theorem. Now think about, let's say, this particular setup over here, right? Now, if you think about this whole space over here, what do you think is the main posit, right? What is the main posit? So over here, the positions are like the elements that you have to cover, right? In fact, not all positions, only the positions that have a or makes sense, right? These are, let's say, the main elemental positions or the sets elements that needs to be covered, right? So now we know that from this you can go this way, and anywhere in between two you can change the path, right? So for a particular space that has an orb over here, you can go to any particular element in this part, right? Right. So if you are over here, you can go to any element over here. I mean, sort of. So you will always have a relation between, let's say, if I just quickly go over between these two elements, between these two elements, between these two elements, right? So they would be like related to each other, right? There would be a relation between them, right? There is a relation between them because you can, from this you can cover to this. So in this question we are defining this as, can you cover the other B element after covering an A element? Let's say this is what the meaning of this is, right? And essentially what we are looking at in this problem is to like take chains where you can cover this after this, and you can cover this after this after this, and this after this, and this after this. So that's one chain. And what we need to do, one chain is like one path, right? And we need to decompose the whole set of orbs over here into multiple different chains, right? So in this case, this becomes like a problem of again decomposing the whole problem into chains. And that's exactly where Dilworth theorem comes into picture. Now Dilworth theorem says that finding minimum number of chain decomposition of the set is equivalent to finding the maximum anti-chain over here. So what is an anti-chain? What are not related? So if this element is related to something on this part, right? And obviously something on this part also is related, then this element will be related to this, right? So this element is not really related to something on this side and on this side, right? So let's think about an orb that is placed over here, right? Over here. Now this is kind of related to any element that is in this part, okay, and in this part, but it's not related to anything in this in this part and on this part, right? But this much and this much is something that it cannot get related to, right? So they are all so these elements like this with any element on this side will not be related, right? So what we need to like kind of think about is like there might be one element which you pair it with. Now if you have taken these two elements, now the new set of like elements that you can take in the same anti-chain are in this, right? So you can get an idea that we are trying to see some sort of like set of points that are in a diagonal setup, right? Like in this case, the largest antichain that I can find of is, let's say, taking up this element, right? Now then taking this element, right? Now taking this element and then taking this element. You can check that none of these elements are related to each other. None of, so because since they are in like this cross space, they are not related, neither these two, neither these two. So the largest antichain in this case is of size 4, and if you remember over here too, we found out the answer to be 4, right? So how do you find out this largest antichain in this case? Very, very simple. If you have studied a little bit of DP, you can use dynamic programming to solve this problem. Let's say if you are starting at a particular thing, you can find out what is the largest anti-chain that you largest chain of nodes that you can form which are not related, or largest anti-chain ending at this node. So I can try maybe like formulating in this way, like loop in this order, and when I reach at this particular node, let's say this contains an orb, so we will let's say with or without an orb, I will just try to calculate this, that what is the dp of I comma j will tell me what is the largest anti-chain in this scope. This is I, this is j. So in from the range n I till n, and in the range 1 till j. In this range, what is the largest set of antichain that you have formed, right? And we can loop in this order. How do we calculate this dp? Very, very straightforward. How do you think you will calculate this dp? We can actually just use this, right? That to calculate the like the answer at this place, what is the largest antichain that is in there? Either that chain lies in this much scope, or it lies in this much scope, or if there is an orb over here, right, then this can combine with anything in this space. So we can use that standard dp of I comma j will be equal to max of dp of I minus 1, sorry, I comma j minus 1, dp of I plus 1 comma j, and then if this particular cell is an orb, you can write all those conditions over here. If this cell is an orb, 1 plus dp of I plus 1 comma j minus 1, and that would give you the like maximum antichain over here, and that chain can be combined with this because none of the elements would be related, right? So that way you can find the largest antichain. Dp of like 1 comma n is going to give you the largest antichain in the whole of this grid, and that is going to be your answer. So this dp is like an order n into m kind of dp to calculate. This should be fairly straightforward. So Dilworth theorem is already a tough thing, so I'm not getting into details of these calculations. I'm assuming that you would be able to calculate these dp on your own. If not, there is a full dp workshop that I've taken on this channel. Go check out those videos, cover dp, and then this should be fairly straightforward for you to cover. But this is what we can do in this kind of a problem, right? So this is what Dilworth theorems allows you to do. Okay. Let's get through one more style of Dilworth theorem questions that I've seen coming up in contests, which is based on a general version, or DAG. That let's say you have some relation given among n elements, right? So let's say there is n elements given to you, and you are given some custom relations that okay, 1 is related to 2, 2 is related to 3, and so on, so right? Some graph is given that let's say 1 is 2 and something like this, and 2 is related to 4, and things like this. So there is a custom posit defined for you, right? And we need to now decompose this into minimum number of chains. Let's say over here, if I take this, I can try and decompose this into this one chain. Okay, then this has to be a separate chain, then this can be one chain, this can be another chain, and this can be another chain. So you need 5. So minimum number of chain decomposition of this particular like posit would be 5, right? Okay, so now how do we find out this answer over here? Because I can very straightforward like see that this is not related to this, and they are also not related to this, and this, right? So this all five form an anti-chain, and we can say that the answer is going to be 5. Now the question that you might be given in is, let's say, find the like chain decomposition, minimum number of chains needed to decompose the whole graph, and print the decomposition maybe. So print 1 3 4 5, then 2, then 9 6 7, then 8, then 10, and something like that. So you have to print the chains too. Okay, so that kind of problem could also be asked potentially. So that is what is like something we can also solve. This is generally the general version of Dilworth theorem, and the way to solve this, okay, if you have not seen this before, I don't expect you to already know this technique, but if you want, you can pause the video and think about this. This particular version is generally solved using something called as flow, right? So I'm going to assume that you know a little bit of flow. If not, please read about it. But the way we solve this particular problem is we take the 10 nodes that are given to us and just connect a source to all those 10 nodes and a sink to all those 10 nodes, right? So there is like copy of this can be like out and this can be in of some particular node, right? So these are out nodes and in versions of the things, something like that. And let's say if there is an edge or a relation between 2 and 4 like this, we connect uh, 2 to 4, right, like this with a flow of 1. Okay, if there is a connection between 1 and 2, so we will connect 1 to 2. If there is a connection between 1 and 3, we'll connect 1 to 3, right? So something like this, and then 3 to 4, right? Whichever edge exists, we will connect that particular 2 nodes from in to out, right? So that's how we will do it. 4 to 5, so 4 to 5 over here. Okay, then over here like 9 to 6, 9 to 8, 9 to 10, then 6 to 7, 8 to 7, 10 to 7. All of these are going to be edges of weight 1. Okay, and then what we do in these kind of problems is, like, once we have built these edges, like I've just drawn all the things a little more clearly, we just, and all of these green edges are also of flow size 1, right? We just find out the max flow. We just find out the max flow in this case. Just run any max flow algorithm, preferably a Dinic, right? I'm going to explain why Dinic should be preferred over here. Or you can also, so this is more like a bipartite matching, so you can also run Hopcroft algorithm in this case, and that should be straightforward to find out the maximal matching over here. And if you understand what is going to be the number of chains, right? So let's say you find out a matching, so I'm gonna just print out one matching. Let's say this matches with this, 2 matches with 4, right? 3 like 4 is already taken, so this edge is now full, so this will go like this will go like this, right? Then 4 to 5 is possible, right? Then this to 6 to 10 is possible, right? Then you cannot go into 7 8 because 10 is already blocked over here, right? Then you can go to 9, and I can go to, let's say, 6 itself over in this case, right? And over here from 4 to 5 was also going a flow of this. So you can see that we had got a flow of 5 sort of over here, right? We got a flow of 5. Now, do I say that whatever is the flow is the maximal matching, is the final answer? No. The answer is always going to be equal to the size of set minus the flow. Okay. This is going to be the minimum chain, or I would say the size of maximum anti-chain, right? Because why exactly like this? Why exactly like this? Because, or this would be the minimum number of chains. I would say this is minimum number of chain. Okay, and this is going to be number of set elements in set minus the flow that we got. Number of elements in set is 10 in this case, flow we got as 5, so answer is 5, which was correct, which is correct, right? We did discuss that the final answer in this case was actually 5, right? We did had these 5 elements in the same anti-chain, maximum anti-chain. So answer is 5. But why exactly is this true? Why exactly is this true, right? So let's try to understand it with some examples, and I'm gonna like kind of run a different versions over here. So let's say had the algorithm would have taken, let's say this, okay, 2 to 4, 4 to 5, 6 to 10, 9 to 6, right? This was what it took. So what it corresponded to over here now is very like simple idea. 1, so this edge, if it's taken, that means 1 and 2 are in the same path. So this is what it takes. Take this chain, okay? Then 2 to 4 is in the same path. Then 4 to 5 is in the same path, okay? That's what this is saying. 6 to 10 is in the same path. 6 to 10, oh, this should have been 10 in that case, right? I think we had a misprint over here. Okay, I think this node should be named 10. This node should be named 7. But yeah, I hope you got the idea. I think I should correct that up in the previous slides too, right? This is 10 and this is 7. Yeah, this is 10, right? Yeah, obviously, like 6, 7, 8, 9, 10, right? So coming back to this, so 6 to 10, so these two belong in the same path and these two belong in the same path, right? So 9 to 6, right? So this means we have decomposed this into one path, this into another path. This is what the path kind of built up, and these whatever are left are actually the independent chains. So if you see what did not get matched over here, 1 did not get matched, 3 did not get matched, 7 did not get matched, 8 did not get matched, right? And 9 did not get matched. So you can see that 1 is actually the start of a chain, 3 is the start of a chain, 7 is start of a, sorry, I should go this side, 7 is start of a chain, 8 is a start of a chain, 9 is a start of a chain, right? And every other edge tells you where to follow from that particular node. So these nodes have an out degree, right? Which means, and these nodes have some in degree. So the nodes with in degree equal to 0 are the start of the chains. And the max, so when we are maximizing the flow over here, right, we are trying to connect more number of nodes, which means the least, we are trying to match as many nodes as possible. So the minimum number of nodes will have in degree equal to 0. And when minimum number of in degree equal to 0 cases are there, that means that many only number of chains will start, right? Whatever will have degree 0 will have a chain starting from that node. So if we minimize the number of in degree 0 nodes, that means we are trying to minimize the number of chains, or that's what is giving us the maximum anti-chain, right? So this is what we are able to solve with using a flow. Just take another example. Let's say if this took the path 1, 2, 3, then let's say 2 got matched with 4, 4 got matched with 5, then 6 got matched with 10, and then 9 got matched with 7. Okay, if this would have been the case, then we would have 1 matched with 3. So this is one path with one chain. Okay, then 2 to 4, 4 to 5. See, 2 to 4, 4 to 5. This is another chain. See, 2 has 0 in degree, 1 has 0 in degree. These are two start of the chains, right? Then you have like 6 going to 10, so this is one chain. Okay, then 9 going to 7, 9 going to 7 is another chain, right? And 8 is an independent chain. So you can see that 6 is left, 8 is left, and 9 is left. So these are the starts of the chain over here, right? So like with the flow in the left hand side, you can easily get the final graph that after the flow has been ran, and with forward flow minus the reverse flow, you can find out which all edges were actually used, and from that you can like derive which all nodes would have in degree equal to 0, and these would be the edges in the final graph, and from that you can actually bring out the paths if you want to, right? So that is the way to solve this general version, and this would actually be possible to solve in E plus V root V, because this is the complexity of, let's say, Dinic, right? If you use Dinic algorithm on a unit flow graph, right? Unit flow graph with a bipartite setup. Had it been just unit flow graph, it would be E plus V root E, right? You can also use, I think, Hopcroft-Karp, which has E root V complexity, as far as I remember, right? So that's a fairly good amount of like complexity to kind of pass in general anything in such sets, right? Because you would have like n number of elements, and E can be on the worst case number of V square, right? So in that case, you would have this as n again. So on the worst case order n square, right? Which is good enough in such setups, right? So that would be almost all there is to this particular thing. So this would be n square, this would be n, so this would come out to order n cube, right? A cubic complexity for this kind of a setup where you have like all possible edges being added. But that is also fairly good enough to solve most questions where you have a general setup. The constraints would be around 500 or so. So that should be good enough to solve. Okay. Now that's there for this particular thing. Let's like quickly close this up. I don't want to like kind of extend it very further. I would give some problems below this to kind of practice on Dilworth theorem so that you get full solidity on this concept. But Dilworth theorem essentially says that the maximum anti-chain equals the size of the minimal chain cover, right? We are interested in this and we convert it to this particular finding, right? There is another theorem called Mirsky's theorem, which is exactly the dual of this, which is essentially like a counterpart to this, which is maximal chain is equal to the minimal anti-chain decomposition of S. And just to visualize what these mean, right? So if you see this Dilworth theorem, we are trying to decompose it into paths, right? So over here, there would be this path, right? We might try to cover this with a path, and then we might want to cover, where is this? Let's take something else, this as a path, right? This as a path, another path, right? Something like this, right? I mean, you don't even need to take a node twice. So in 3 you can do it, right? In fact, if you try to find out the maximum anti-chain, it's nothing but in these 3 paths, if you try to find out like a set like this, which are like in different paths and there is no relation between them, you can find out the maximum size as 3. So it's like width on this line, right? This is like the width and this is like the length, sort of, right? Width and depth, right? The Mirsky theorem is opposite. Mirsky's theorem says that we are interested in the maximal chain, which means the depth has to be highest, right? The maximum number of nodes in the same chain. So it's like this particular node over here, right? Okay. And this is the size of minimal anti-chain cover of S. How would you find out an anti-chain cover in this case? So what we can do is we can take this node in one anti-chain, right? Then this node, these two nodes in one anti-chain. Then maybe like this is layer number 2, this is layer number 1, this is, let's say, layer number 3, this is layer number 4, this is layer number 5. You can see that no two nodes in the same set is actually the part of a particular like there is no relation between the elements and it's a proper anti-chain. So in this case we are like having a minimal, so this is the minimum number of like anti-chain covers that you require, and it's actually equal to maximum chain. And in such problems you can actually find the longest path in DAG very easily. So this side of the equations are generally easy to find. This is longest path in a DAG. This is nothing but as we kind of talked about, maximum group of elements where there is no relation. So essentially it's like in a graph, in a complement graph, it has to be a clique, sort of, right? So maximum size clique in the complement graph. So these things are fairly straightforward to find out. This side of the equations is what the problem would be in. You will have to transpose this to this side. Okay. Another particular corollary that is there on this particular topic is this one, which is Algos Securus theorem. Okay, which is essentially like if you have these many number of set elements, right? Then either there is an increasing subsequence of this or a decreasing subsequence of this much. And this is something we are not going to prove. I'm going to give the link to proofs of these theorems that we talked about. There is a very nice, brilliant prog that you can kind of refer to if you're interested in proofs and stuff. But essentially, this is just like saying that there is a, so we said that this was width, right? The increasing subsequences sort of might mean width, and this is sort of the decreasing subsequences of length s plus 1 would be height, right? And we are essentially saying the area is actually equal to r into s plus 1. Okay, so either this has to be greater than equal to r plus 1 or this has to be greater than equal to s plus 1, right? And this is obviously not a formal proof, but essentially like just this being less than equal to s and this being less than equal to r will not work. One of them has to be greater than equal to like the other part. That is how we can also visualize this particular theorem. It's also a good one. Might be used in some question someday. I'm not sure though, right? And that's almost all about Dilworth theorem that you need to know, right? Now, quickly talking about the sponsors for this video is sponsored by Algos. So they have different sets of running that the courses that they had been running on competitive programming and specifically for cracking coding tests and interviews. Now, 202 has now been merged into 201. 301 is no longer running, and it's like a separate camp for senior folks who are preparing for ICPC and generally the world final side of things once they complete 201. What this training is really good at is teaching competitive programming and again cover the interview stuff that is required. So most of people in India at least happen to have internships placements coming up in July and also want to push up their rating. So there is a 16-week of intense, let's say CP training. When I say intense, the topics names might look very simple, but it's very, very intense. This is mostly what I take as a live educator. Then there is this 3 to 4 to 5 week of interview boot camp where we talk about like core CS fundamentals like operating systems, networks, and things like that. And it's like it contains 500 plus highly educational problems on its own platform. There is a separate online judge for that. Quant and HFTs, which are like really the hots and companies that are coming up these days in a lot of IITs and hiring for crores of packages. That's also something that we train people for. Core CS is something that we also cover a little bit. I mean, mostly the gist of it that is required for interviews. Project is something that is being built in the course of Algos nowadays. Like you get two awesome project built so that your CV looks a lot good than any standard CV where you have basic projects like Sudoku and stuff like that. Nowadays, like people have moved beyond this, right? And like there is day wise target where I have to solve, and there are like good amount of minimal problems, standard problems, and achiever problems that you have to go through, right? And a new batch is starting from 12 December. So if you are willing to join that up, definitely check that out. There is a coupon code in down below. You can use that coupon code to get a discount, but only if the first 20 people who gonna like sign up with that particular code is gonna get it. So hurry up before that finishes up, right? So that's all about the sponsors. Thanks for joining in for this video. I hope you liked the content on Dilworth Theorem. We will keep doing more and more such stuff on many different competitive programming ideas. And if you are interested in learning these, do subscribe to the channel and press the bell icon so that you don't miss out on those. And in the next video, we'll learn something more interesting again. Till then, see you. Bye bye.